Before we formally start our topic, let us first define what is problem solving and reasoning. Problem solving is the process of finding solution to difficult or complex issues, while reasoning is the action of thinking about something in a logical, sensible way.
So, good day everyone. I am Lorraine Malabor from BE Ed 12, and today we will tackle about the inductive and deductive reasoning. So, what comes into your mind when you hear the word inductive? What is inductive reasoning? Inductive reasoning involves moving from specific instances or observations to broader generalizations. It relies on collecting evidences, patterns, or trends from the specific cases and using them to make probabilistic or plausible conclusion about a larger set of cases or the entire population. Francis Bacon is credited with introducing the inductive reasoning into scientific inquiry in the 17th century. His theory was that scientific knowledge must come from the careful observation of natural filtered through inductive reasoning. Presented on the screen is one example of inductive reasoning. The sun has risen every morning throughout history. Therefore, the sun will rise tomorrow. This example showcases inductive reasoning by extrapolating from past observations of the sun rising to predict that it will continue to rise in the future. We surveyed 1,000 people across the country, and 520 of them said that they will re-elect the mayor. We estimate that 52% of the country will vote to the mayor and he will be re-elected. So this is an example of inductive reasoning because many statisticians make a living from conducting tried and true inductive reasoning studies. We often call it a pooling data. So pools will look at a sample sizes that is often large enough to have a 95% probability of being correct. We are now done on discussing about the inductive reasoning, and on the other part, we will talk about the deductive reasoning. Are you ready? So, deductive reasoning is also known as a top-down reasoning because it is a logical process that involves drawing specific conclusion based on general principles or premises. So, Aristotle is a Greek philosopher who is considered as the father of deductive reasoning. So, he started documenting deductive reasoning in the 14th century. He believed that it is a form of reasoning that begins in the sense of perception of particulars and ends in an understanding that can be expressed in universal proposition. So, presented in the screen are some examples of deductive reasoning. So, the first example: all men are mortal. Socrates is a man. Therefore, Socrates is mortal. The first premise states that all objects classified as men have the attributes mortal. The second premise states that Socrates is classified as a man, a member of the set men. The conclusion then states that Socrates must be mortal because he inherits these attributes from his classification as a man. So the last slide will tackle about the pros and cons of deductive reasoning. On the left side is stated the pros of deductive reasoning. So first, when you have a big enough sample set, conductive reasoning is highly accurate in developing general ideas. Second, inductive reasoning enables us to model big phenomena that are impossible to directly measure, such as how many stars there are in the universe. On the other hand, are the cons of deductive reasoning. So, inductive reasoning can lead to incorrect outcomes, especially when the data set is too small to be an accurate representative of the whole. So, Second, or the last statement, is that the more generalized and assumptions become, the uses likely they are to be accurate.
Good day, everyone. I am Lovely Heart Alvarez. So, in the previous video, we've tackled about inductive and deductive reasoning. So now we're going to discuss about intuition, proof, and certainty. Intuition is a mathematical belief without being formalized and proven directly and serve as an essential part of mathematics. So, the word intuition carries a heavy load of mystery and ambiguity, and it is also somewhat dangerous, a legitimate substitute for a formal proof. Intuitive is the counterpart of rigorous. Being rigorous is not completely clear and never gives precise meaning. Intuition is the ability to understand something immediately without the need for conscious reasoning. When we do intuition, we are explaining or justifying a thing based on our own perspective or our own principle. When we say intuition, it is something what we understand directly through our minds. It is what we believe directly without any formalization or without any proven truth or proven evidences that will support our statement. It was just the way we think immediately. So now let's move on to what is conjecture. So, conjecture is an approved proposition that is believed to be true. Proof is important to mathematics. If one has conjecture, the only way it can surely be true is by presenting a valid mathematical proof. Being able to write down a valid proof may indicate that one has a thorough understanding of the problem. Di ba, dili ta mo to og mga butang nga wala ebidensya. Like, we need proof to testify our intuition. In mathematics, we really need proof because it is an evidence or an argument establishing or helping to establish a fact or truth of the statement. In mathematics, a proof is an inferential argument for a mathematical statement. In mathematical statements such as theorems can be used if it is already proven. So, in principle, a proof can use axioms which are denoted as self evident or assumed statements along with accepted rules of inference. So, now let's move on to certainty. What is certainty? Certainty is the quality of being reliably true. It is the state of being definite or of having no doubts at all about something. We know that the need for certainty is inherited from ancient past and it's religiously motivated. Its validity is independent of its history and motivation. But in mathematics, there is no problem of being certain, for certainty is just essential defining attribute for mathematics and mathematical knowledge.
Hello, so let's move on to Polya's 4 steps in problem solving. Okay, one of the foremost recent mathematicians to make a study of problem solving is George Polya. He strongly believed that the skill of problem solving can be taught, and the most efficient way of learning mathematical concept is through problem solving. The students and teachers become a better problem solver. So he developed the framework known as Polya's 4 steps in problem solving. So the basic problem solving strategy that Polya's advocate consists of the following 4 steps. So what are those 4 steps? First, understand the problem. Second, devise the plan. Third, carry out the plan. And lastly, look back or review your answer. Okay? In order to become a good problem solver, we should follow Polya's 4 steps, which help to examine each of the steps and determine what is involved. Usually, a mathematical problem is presented in words, whether orally or written. We will solve the mathematical problems using mathematical symbols and then interpret the answer. You can see in the figure 3.1, the process of problem solving. So, here are the 4 steps in order to solve the problem. Step 1. Understand the problem. Sometimes, the problem lies in understanding the problem itself. To help us understand the problem, we might consider the following. What is the goal? Unsa man siya goal? Ani? Unsay target? What is being asked? Unsay gipangutana? Kung pwede lang, balik-balikon o basa ang question para mas masabtan. Bisayon nimo, para mas makasabot ka. What is the condition? What sort of a problem is it? What is known or unknown? Is there enough information? Can you draw a figure to illustrate the problem? Is there a way to restate the problem? Step 2. Devise a plan. Devising a plan or translating is a way to solve the problem by picturing how we are going to attack the problem. Ani ta maglista sa mga possible nga plan. Act it out, be systematic, work backwards, consider special cases, eliminate possibilities. Mag-iingon, make a list or table or chart. Draw a picture or diagram. Then, here we are going to guess and check our answer. Trial and error. The third step is carry out the plan. In carrying out the plan, we need to execute the equation we came up in step 2, which is the devising a plan. The main key is to be patient and careful, even if we have necessary skills. We should be patient and work carefully. And modify a plan. If ang plan mo ay hindi successful, you need to have plan B. Try and try until you succeed. And the last step is look back. Look for an easier solution. This step help in identifying if there is a mistake in the solution. It is time to reflect or review and look back what is done, what worked, and what didn't. Does the answer make sense? Is your answer make sense? Check the results in the original problem. Interpret the solution. Recheck. We should ensure the consistency of the solution in the context of the problem. Ensure that all the conditions related to the problem are met. So review if your answer is correct. So we have here some examples. Suppose the NCAA basketball championship is decided on a best of 5 series game. In how many different ways can a team win the championship? So, ang first step is understand the problem. What is being asked? So, ang question, no? In how many different ways can a team win the championship? No. So, there are different ways, no, can a team win the championship. The team may have won 3 straight games, or maybe they could lose the first 2 games and won the last 3 games. There are also other possibilities such as win-win, lose-win, win-lose, win-win, and win-lose, win-lose, win. So, step 2, devise a plan. Make an organized list of all possible orders and ensure that each of the different orders is accounted for only once. No. Step 3. Carry out the plan. Each entry in the list must contain 3 wins and may contain 1 or 2 losses. Use a strategy to each order. One strategy to start to write win or W, then write L or lose if it is not possible to write W. This strategy produces 10 different orders shown below. Yan. So you can see in the picture, no? It is the possible list of the team could win the NCAA championship in the best of 5 games. And the last step is look back. So the list above is organized and contain no duplication. It includes all possibilities. We can conclude that there are 10 different ways in which a basketball team can win the NCAA championship in the best of 5 games. So we have here another example. 2 times a sum of a number and 3 is equal to thrice the number plus 4. Find the number. So, step 1, understand the problem. So, we need to make sure that we have read the question carefully several times since we are looking for a number. So, we will let x be the number. Step 2, devise a plan. We will translate the problem mathematically. 2 times the sum of a number and 3 equal to thrice the number plus 4. No. So, step 3, carry out the plan. We solve for the value of x algebraically. 2x plus 3 close open parenthesis equals 3x plus 4. So, 2 times x equals 2x plus 2 times 3 equals 6 equals, copy 3x plus 4. So, copy 6 expose 4 equals, copy 3x and expose 2x. 6 minus 4 is 2. And then 3x minus 2x equals x. So therefore, the x is 2. Step 4, look back. If we take 2 times the sum of 2 and 3, that is the same as thrice number 2 plus 4, which is 10. So this does check. Thus, the number is 2. So now let's move forward to mathematical problems involving patterns. Numbers are everywhere in our daily lives. Ethics is based on numbers. Mathematics is useful to predict, and number pattern is about prediction. Number pattern leads directly to the concept of function in mathematics in relation to different quantities, which is defined as a list of the numbers following a particular sequence. Number pattern can also be applied to problem solving, whether a pattern is present and can be used to generalize a solution to a problem. Pattern can be in the form counting up or down, and the missing number is the form of completing count up or down. One of the most number patterns: 0, 1, 2, 3, 5, 8, 13, 21. The Fibonacci sequence. There are 4 types of pattern, which are prime number pattern, imaginary number pattern, geometric number pattern, and growing number pattern. What is infinite sequence? Infinite sequence is a function whose domain is the set of positive integers.
So A1, A2, A3, A4, and so on, A number -1, A number, and so on, are terms of the sequence. So if the domains of the function consist of the first and positive integers only, the sequence is a finite sequence. So example number 1, identify whether the following are finite or infinite sequence. So A, 1, 2, 3, 4, 5, 6, 7. B, 2, 4, 6, 8, 10, 12, 14. C, 1, 3, 5, 7, 9, 11, 13, 15. D, 3, 6, 9, 12, 15. E, 1, 1, 2, 3, 5, 8, 13. F, 1, 4, 9, 16, 25, 36. So the first 3 letters with the sequence are some examples of finite sequence. The other half from D to letter F are some examples of infinite sequence. So a general sequence, A1, A2, A3, and so on, AN -1, AN, and so on, having the first term A1, the second term is A2, the third term is A3, and the nth term is called the general term of the sequence is AN, or A number. Example number 4. Determine the nth term formula for the following polygonal numbers in the nth figure. A, triangular number, B, square number, C, pentagonal number, and D, hexagonal number. So, solution. We first defined what polygonal number is. So, a polygonal number is a type of figurative number represented as dots or pebbles arranged in the shape of regular polygons. So, A, triangular number. So, there are pictures presented in the screen, and that is one example of a triangular number. So, observe that the number sequence is n is equal to 1 is 1. N is equal to 2 is 1 plus 2 is equal to 3. N equals 3 is 1 plus 2 plus 3 is 6. N is equal to 4 is 1 plus 2 plus 3 plus 4 equals to 6. N is equal to 5 is 1 plus 2 plus 3 plus 4 plus 5 is equal to 15. And N equal to 6 is 1 plus 2 plus 3 plus 4 plus 5 plus 6 is equal to 21. Which can be generalized as T n is equal to 1 plus 2 plus 3 plus and so on plus n minus 1 plus n is equal to 1/2 and n squared plus n. Expanding the triangular number sequence 1, 36, 10, 15, 21, 28, 36, 45, and 55, and so on. Second example is the square number. So,
Observe that the number sequence is n is equal to 1, so 1 squared is equal to 1. N equals 2 squared equals 4. N equals 3 squared equals 9. N is equal to 4 squared is equal to 16. N equals 5 squared is equal to 25. And N equal to 6 is 6 squared equals to 36. So which can be generalized as Sn is equals 1/2 and 2n squared minus 0 n is equal to n squared. Expanding the square number sequence 1, 4, 9, 6, 25, 36, 49, 64, 81, and 100, and so on.
And now, let us move on to our last topic, which is recreational problems using mathematics. So, what is recreational problems using mathematics? Some of the well-known topics in recreational mathematics are Rubik's Cube, the magic squares, the logical puzzles, the fractals in mathematical chess problems. But area of mathematics includes aesthetics and culture of mathematics, peculiar or amusing stories and coincidences about mathematics. So that is recreational problems of mathematics. Recreational mathematics is a carried out mathematical activity which involves mathematical puzzles and games. So some of the topics are as what I have mentioned, the magic squares, and the culture of mathematics, and etc. One of the ancient square mathematic recreation of all is the magic square. A Chinese myth on the time of Emperor Yu came across a sacred turtle with a strange marking on its shell known as Lucio. The markings are numbers and they form a square patterns of order 3. And in 1514, the artist Albrecht Dürer made an engraving Melancholia containing square pattern of 4. Let's talk about Lucio first. Lucio is also known as the magic square. There is the interaction of the numbers within the square. The sequence of the numbers is considered to be a natural movement in nature. So, what does that mean? The interaction of the numbers within the Lucio square. Even numbers are at the corners of 2, 4, 6, and 8. The odd numbers form a cross in the center of the square. The number 1, 3, 7, 9 at the edges and 5 in the center. The sums of the corners sums to 10, whereas 4 plus 6 is equals to 10 and 8 plus 2 is equals to 10. The sum of the edge also sum to 10. 9 plus 1 is equals to 10 and 3 plus 7 is equals to 10. The sum of the 3 rows and the 3 columns all sum to 15. Another property is the combinations of numbers that subtracts to 5. On the top left, 9 minus 4 is equals to 5. In the top right, 7 minus 2 is equals to 6. In the bottom right, 6 minus 1 is equals to 5. In the bottom left, 8 minus 3 is equals to 5. These numbers are frequently represented in the format of this diagram. In the 1514, the artist Albrecht Dürer made an engraving Melancholia containing square pattern of order 4. Melancholia is a large 1514 engraving by the German Renaissance artist Albrecht Dürer. Its central subject is an enigmatic and gloomy winged female figure thought to be a personification of melancholia or melancholy. Dürer's magic square has an additional property that the sums in any of the 4 quadrants, as well as the sum of the 4 numbers, are all 34. It is thus a Neumann magic square. In addition, any pair of numbers symmetrically placed about the center of the square sums to 17, a property making the square even more magical. What is the Neumann magic square? It is a 4 times 4 magic square in which elements in each 2 times 2 corner have the same sum. Dürer's magic square, illustrated here, is an example of a Neumann magic square, since the sums in any of the 4 quadrants as well as the sum of the middle 4 numbers are all 34. That is why it is called Neumann magic square. Palindrome is a number or word or phrase, sequence of characters or symbols which reads the same backward as forward. For example, 131. When you read it backwards, it's still 131. That is an example of palindrome. Here is an example of recreational mathematics, the Tower of Hanoi. Tower of Hanoi is a logical puzzle frequently studied in cognitive psychology, and it is used as a test of problem-solving ability. It consists of 3 rods and a number of desks of various diameters which can slide into any rod. The puzzle begins with a desk stuck on one rod in order of decreasing size, the smallest at the top, thus approximating a conical shape.